Hi guys, welcome to our newest video for our synoptic meteorology class. In the previous videos, we talked about atmospheric stability, hydrostatic balance, and hydrostatic equation, as well as geopotential and geopotential height. But in this video, we'll be talking about cloud development. So, when we are talking about cloud development or how clouds are formed, we should recall one of the most basic and yet significant ideas when it comes to atmospheric stability. So, in an unstable atmosphere, a lifted air parcel will be warmer than the air surrounding it, thus making it less dense, and thus will continue to rise upward away from its original position. So, if this air parcel continues to move up and reaches a saturation point, it will condense and form clouds. So that's what we will be talking about. So in the first video, we talked about the triggers or when an air parcel is pushed in an unstable equilibrium, it will accelerate away from its original position. So in cloud development, what are the triggers of cloud development? First, we'll be talking about surface heating and free convection. Next, we'll be talking about uplift along topography. We also have convergence of surface air as well as uplift along weather fronts. Okay, so here are simple diagrams of those four triggers or mechanisms for cloud development. Diagram A, we have convection. Diagram B, we have lifting along topography. We also have convergence of air, diagram C, and diagram D, lifting along weather front. So we'll talk about these mechanisms separately later on. So we know that some areas of the Earth are better absorbers of heat. So we can call these surfaces as hotspots. The air above these hotspots become warmer than the surrounding air. So what does it do? So it becomes a hot bubble of air, which then we can call thermal. So this thermal breaks away from the warm surface and rises, expanding and cooling as it ascends. So you may think that a single thermal um, is already enough to form a cloud or a cumulus cloud. We need subsequent thermals to raise the air a little higher. So subsequent thermals rising in the air forming clouds. If it reaches saturation, condensation occurs, then the thermal becomes visible as a cumulus cloud. So you can see in the diagram blue arrows going down. So why is there a downward motion? So there are two causes or there are two reasons why there is a downward motion for the thermal. Number one, it's caused by evaporation along the edge. So we know that evaporation is a cooling process. So when the edges cool, then it becomes more dense than the surrounding. Then what will it do? It will sink. And the next mechanism is that, or the next reason is that there's a completion of the convection current. So as you can see, the red-orange arrow going up, and as it reaches the condensation level, um, it will cool down and will then again sink. So we can say that below and within the cloud, the air is rising, but in the edge or at the edge of the cloud, the air is actually sinking. So in this diagram, I'm showing you that this shows cloud formation with regards to atmospheric stability. So stability of the atmosphere, as we know, plays an important part in determining the vertical growth of cumulus clouds. So if there is a thermal that became a cumulus cloud will it propagate? Will it develop into a more um, into a yet bigger cloud that will produce precipitation? So it depends on the stability of the atmosphere. In diagram A, you can see that um, it's stable at the top or above the cloud top. So the cloud is not able to rise. So this happens when there is an inversion. So when we say inversion, as you go up the atmosphere, the temperature rises. So we are talking about the troposphere. So inversion happens usually early morning, as I've mentioned in the previous video. So this kind of stability or atmospheric condition produces what we call cumulus humilis, or these are actually what we can call fair weather clouds, or clouds that you can see obviously during fair weather. In diagram B, we have another cloud. It's cumulus congestus. If the atmosphere has deep conditionally unstable, or if the atmosphere is deep conditionally unstable, it will form cumulus congestus. So we'll know more about that. I'll show you an actual picture later on. But then if the atmosphere is conditionally unstable for miles deep, it can form cumulonimbus clouds with the anvil top. Okay, so to give you an actual idea of what these clouds are, this is what cumulus humilis looks like. So the fair weather cloud. So when we see this, we can say that we'll be having a fair weather, a good weather within the day. Next, we have cumulus congestus. So again, for the previous cloud, the cumulus humilis, cumulus meaning puffy, low and puffy, fair weather, and humilis means flattened and it's wider than it is tall. So for cumulus congestus, we have clouds with cauliflower-like tops. So if you know cauliflower, you can very well imagine the cumulus congestus. Okay, so moving on to cumulonimbus incus. So when we say incus, it's a Latin term for anvil, shaped as such because it has reached the stable part of the atmosphere. So it can no longer penetrate more or deeper into the atmosphere. They cannot grow further vertically, so it grows laterally. So you can see that it has grown wider than taller. So that's cumulonimbus incus. And so that's for convection and cloud. So how about topography? Topography. So obviously, horizontally moving air cannot go through a large obstacle like the mountain in the picture. So what does it do? Obviously, the air must go through or must go over it. And so, force lifting along topographic barrier, that's called orographic uplift, and it can produce clouds. Clouds produced by this manner are called orographic clouds. Here I'm showing you a diagram of an example of orographic uplift and cloud development. You can see that the air from the windward side is force lifted. It produced clouds starting at an altitude of 1 kilometer up to the top of the mountain. Notice that the air at the leeward side is considerably warmer than the initial temperature because the latent heat was converted to sensible heat through condensation, which we know condensation is a warming process. Also, you can see that there is actually a decrease in dew point temperature. So the decrease in uh, dew point temperature can be attributed to the rapid decrease in air pressure of the rising air. So TD, or dew point, is directly proportional to vapor pressure. So meaning if the vapor pressure decreases, there is a corresponding decrease in dew point temperature. So these are two concepts to remember with regards to orographic lifting. Number one, air descending a mountain warms by compressional heating, and upon reaching the surface can be much warmer than the air at the same level on the upwind scale. The next concept to remember is that air on the leeward side, or the side wherein there is no condensation, there is no cloud or dry, it's normally drier, has a lower dew point than the air on the windward side. The lower dew point and higher air temperature on the leeward side produce lower relative humidity, a greater potential for evaporation of water, and a rain shadow desert. So, as an example of that, I'm showing you a picture of the windward side and leeward side. So, in the windward side, you can see that there is much moisture, there is vegetation, but then on the leeward side, you can see that there is what we call the rain shadow desert. Also, the clouds that form due to orographic lifting. So clouds are more prevalent in the windward side, though clouds may also form in the leeward side. But then clouds that form due to orographic lifting are lenticular clouds. So there are kinds of lenticular clouds. So those lenticular clouds that form in the wave directly over the mountain, these are called mountain wave clouds. Those that form downwind of the mountain are called lee wave clouds. And on the underside of the lee wave crest, a turbulent rotor may form. As you can see in the diagram, there is a wave created by the large obstacle, which is the mountain. So clouds may form in a series of waves extending to several hundred miles. So this can mimic the ripples in the water. So here are actual examples of lenticular clouds. As you can see, this is very familiar to us because we can see Mayon volcano. So if layers between cloud forming layers, as depicted in the diagram, we have dry air layer, we have moist air layer, we have dry air layer, and yet again moist air. If the layers in between cloud forming layers is dry, it will form several layers of lenticular clouds. So you can see at the top right picture, we have two layers. At the bottom right picture, we have so many layers. So I cannot count that. For the layers in Mayon, I think we have two thin layers. So you can see that. Okay. Another interesting example is this picture. So this is an image from NASA Earth Observatory showing a lee wave formed by wind flowing over Amsterdam Island. So this island is located at the southern Indian Ocean. There, that's a very small island, but it creates so much ripple or waves that extends for miles and miles. And this actually looks like a both moving through still water, but in this certain situation, the island is still, the wind is the one that is moving. Next to topography and clouds, we have frontal lifting. I think I've mentioned this in the previous video. Front, a zone of rapidly changing temperature, strong temperature gradient. We have several types of fronts. We have cold, warm, stationary, and occluded front. So for cold advancing front, we can see that if it moves forward, the warm air, since warm air is less dense, it will be pushed up. Then it will produce clouds. And in diagram B, warm air advancing, then you can see that it will be pushed up due to cold air being more dense than the warm air. So this can produce clouds. Next is convergence. So surface air also converges to produce clouds. So when it converges, it doesn't have any choice to go down. So it is forced to rise. So if the air is forced to be lifted up, this will form clouds, as I know that you are well aware. So we'll talk about cloud classification. So we have all the classification of clouds that's divided into four: cirrus, stratus, cumulus, and nimbus. But we have now a new classification of clouds. They can be classified as high clouds, middle clouds, low clouds, and clouds with vertical development. So here is a picture of the distribution of clouds. So high clouds, heights greater than 6,000 meters or 19,000 feet. Middle clouds, heights between 2,000 meters and 6,000 meters. Low clouds below 2,000 meters. Clouds with vertical development may extend through much of the atmosphere. Okay, let's go to high clouds. These are mostly composed of ice crystals. So the principal types are cirrus cloud, cirrostratus, cirrocumulus. So here's a picture of cirrus and cirrostratus. We also have cirrocumulus. For cirrocumulus, there are four defined species. We have Cirrocumulus stratiformis. We also have Cirrus Cumulus lenticularis. We also have Cirrocumulus flucus, and Cirrocumulus castellanus. So these are the four defined species of cirrocumulus clouds. We also have contrails, which are just trails or clouds formed by aircrafts. Next, we have middle clouds. So that's clouds between 6,000 and 19,000 feet. So these are mostly composed of supercooled water. So we have two principal types. We have altostratus and altocumulus. So when we say alto or altum, that means height, and cumulus means heap or puff. So we have altostratus there. So there's no much distinct characteristic. We also have altocumulus. So altocumulus is usually associated with settled weather. Also white and gray with shading. So when we can see altocumulus, do we expect precipitation? None. Next, classification, low clouds. So these are composed of liquid water. So these clouds are closer to the surface. So we have principal types. That's stratus, nimbus stratus, and stratocumulus. For stratus, so I know that you are familiar with stratus clouds. These are featureless low altitude clouds. They are layered, stratus meaning flattened or spread out. So should we expect precipitation from stratus clouds? Yes, but only light precipitations. Next low cloud is nimbostratus. So these are dark gray featureless cloud, thick enough to block the sun. So when we see this, we should expect persistent rain, thunderstorm. Next, we have stratocumulus. So this consists of large, round masses of stratus that form groups, lines, or waves. So we should expect light precipitation from stratocumulus. Next are clouds with vertical development, cumulus clouds. Cumulus clouds can extend up to the entire depth of the atmosphere. Or, yeah, principal types cumulus. We have two, as I've mentioned a while ago. We have cumulus humilis, cumulus congestus. And next principal type, we have cumulonimbus. This picture I've shown you before. So I have cumulus congestus with cauliflower tops. We have cumulonimbus incus, anvil top. So we move to other types of clouds or special types of clouds. First, we have lenticular clouds. Next, we have banner cloud. So located at mountain peaks. This is also a kind of an orographic cloud. So this mountain peak is actually from the Matterhorn in Switzerland. Other special type, the mammatus clouds, balloon-like clouds hanging from below cumulus clouds. So if you see mammatus clouds, then you can say that the atmosphere is really unstable. Next type of cloud, we have the nacreous cloud. So this cloud forms in the lower stratosphere over the polar region. So the sun illuminates the particles in the atmosphere that so we can see very beautiful colors of this cloud. So we should not expect any precipitation from these clouds. So these are very high clouds. Another rare, extremely rare and very high cloud seen in the night sky. This is the noctilucent cloud. So when we say noctilucent, this just means night shining. Nocti and lucent, translucent. Nocti, nocturna. We should not also expect precipitation from these clouds. Next, we have the Asperitas cloud. So this is actually the newest cloud type. This is rare. This resembles rippling ocean waves in the sky. So the Latin aspero means make rough or uneven. So that's a beautiful kind of cloud. We also have this one, Kelvin-Helmholtz clouds. So this forms when there is a difference in the wind speed or direction between two wind currents. So knowing this cloud genera or cloud species, so how do we observe clouds? We have one instrument that we call ciliometers. These are automated instruments that measure the height of the cloud base or ceiling as well as coverage. Both cloud ceilings and coverage is reported in the standard ASOS hourly observation. But we also have manual observation of cloud cover. And we determine that through using this table. We, dev- uh, we measure cloud cover in 8 parts or octas. 0 means clear, 1 over 8 to 2 over 8 means few, 3 octas or 4 octas means scattered, 5 to 7 octas means broken, 8 over 8 means overcast, so meaning the air is completely covered by clouds. Also, we can observe clouds using satellite imagery. So this is now one of the primary tool for observing clouds and its motion. So we have visible satellite imagery, infrared satellite imagery. We also have water vapor satellite imagery. So for example, this one. So we have visible satellite imagery in the Philippines from February 13, 2020 at 8 a.m. or 00 UTC. We also have infrared satellite imagery. So this is what you usually can see from Pag-asa, just to clearly visualize the cloud conditions and the movement of synoptic weather. So this is from the same date and time. We also have water vapor satellite imagery there. So that's it for our video for today for cloud development. So I hope you learned something. See you in the next video.